So we are on to our last topic. So this week, we have 3 lectures remaining. We're going to cover what's called substitution reactions. This is the point where we actually get to be organic chemists. Up until now, we've gotten all the nomenclature. We've got the basics of how atoms work. We've got basic physical chemistry. We've described bonds. We've described changing bonds, acid-base, stability. This is the section where we put it all together. This is the first time we're demonstrating to you guys how you can apply these things, including things like chirality, molecular relationships, naming. This is where rubber meets the road, okay? This is where each component comes together. So what we're going to carry through is, first of all, the general topic of what a substitution reaction is, and then cover these 2 kinds. There are 2 basic ways to execute a substitution reaction, what we call SN1 and SN2. So, first of all, a substitution. This is the general reaction or overall balanced chemistry. A substitution reaction must look like this. This is the generic form. A what we call nucleophile, Nu, will react with some substrate. The substrate is made up of the target molecule and what we call the L or leaving group. It's a bimolecular reaction. 2 things come in, and if you look at what happens here, 2 new products are formed. Most importantly, what used to be this L bond, whatever this R group here was bonded to, we are now bonded to the nucleophile. We have substituted that group. This is why they're called substitutions, because the target molecule, whatever we're saying that R thing is, it has lost the L piece, it has added the nucleophile. So it's this exchange. 1 bond is broken, 1 bond is formed. Now, general pieces, the nucleophile, no matter if it's SN1 or SN2, the nucleophile is a species, a carbon, or some type of molecule, that is negatively charged or has an abundance of electrons. The reason, again, look at the name, nucleophile. Nucleophile means nucleus-loving. It means it is a negatively charged species that's looking for a positively charged center. So anything that we call nucleophile, it must have lone pairs, negative charge. When we're looking at general species, that's the part that helps you to identify it. The target molecule, this piece here, what we're reacting on must have this weak bond, whatever's attaching to this leaving group, that we're going to displace. So not everything is going to qualify as a leaving group. We'll talk through each of these different pieces. But the generics are the same. So more specific, putting actual molecules to this would be a substitution reaction. We have a nucleophile. It's this hydroxide species, lots and lots of extra charge, negative charge around the oxygen. We have the electrophile, the other part of this reaction. The electrophile has 2 specific things. There is what we call the reactive center. This is the carbon where this reaction happens. It's the specific atom where the nucleophile becomes bonded to. So if you have a very, very large molecule, what we call the reactive center, we're talking about the carbon that is currently holding on to the thing being displaced, the leaving group. Now if you look at this too, think back in terms of acid-base. If this was an equilibrium, generally, substitution reactions are not considered equilibria. These are under kinetic control. They're irreversible. But if you look at this reaction both sides, we have hydroxide, O-, and that's going to attack a neutral species, the electrophile. We form a new neutral species. We've got a bond between the oxygen and carbon, the reactive site, right? This is the new bond we formed right here. And we've kicked out another negatively charged species. Just like acid-base reactions, everything is balanced. All the electrons on one side are accounted for on the other. All the charge on one side balances the other. All the atoms on one side balance the other. So this is one of the really, really critical things you have to do when you're watching this. Do not do alchemy. You're not going to create or destroy matter and electrons in this reaction. This is just rearranging bonds. So just like an acid-base reaction, pay attention to where the different pieces are. Notice too, the leaving group, also negative, as is the nucleophile. But if you had to look at these 2 in terms of stability, which is a happier anion? Chloride or hydroxide? Which do you think is more stable? Chloride. Why? more polarized, a more yeah, both of those things. Remember, if I thought of these things in terms of the conjugate base of some acid, the acid from hydroxide would be, if I gave it a proton, what do I get? H2O. Versus I give this guy a proton, I get leaving groups very typically are the conjugate bases of very strong acids. HCl would be your strong acid. Chloride is your leaving group. Iodide would be a leaving group. Like hydroxide, bad leaving group. We'll talk about that in a bit. Yes?
When you're referring to the nucleophile, is it like the whole molecule is the nucleophile or just the charged atom?
The whole molecule. Like this whole thing is called the nucleophile. This whole thing is called the electrophile. Within them, contained in the nucleophile, you might refer to the oxygen as the reactive center in the nucleophile, where the business is happening. But the whole molecule is the term for the entire thing. Just like electrophile is the whole thing, it is made up of a reactive center, the carbon, which will hold on to the nucleophile, and the leaving group, the part that ends up being ejected at the end of the day, right? So there's both pieces and overall names. But these are the things to put your radar up on. Nucleophiles generally are less stable anions. That's what drives this reaction forward. If you imagine basically talking about this in terms of energetics, back to acid base is not directly related, but the same concept comes in. We're going to start with something that is a less happy anion to kick out a more happy anion. So generally, what do you think the delta G naught for this is? Positive or negative? Yeah, negative. It's getting better. The reason that this reaction is driven forward is you're forming a more stable state. You start from less stable anions and make more stable anions. They go forward because you're going to a more stable reaction. That's how we predict these things. So here's another example. Slightly more complicated. This is what we would typically look like. If I was going to go to my notebook, my lab notebook, this is how I would document down the reaction I'm doing. I'm putting a couple things in context here. Normally, as an organic chemist, and this is where you get to actually put all the pieces together. This is Harry Potter class time. This is like what it looks like in spell books. We write this, and what we mean is, this is the molecule I care about because this is what I'm trying to make. I went to the lab because I was trying to build this molecule over here on this side. So typically, we will focus the starting material on one of two components, the thing I started with. Why did I choose this? Because I was trying to make that. So you'll often see this where there's one component and one component highlighted on either side of the reaction. Here, putting things in this position, these are what we call reagents. They're still part of the reaction. They're important to happen. Reaction will not happen without them. But they're shown above the arrow in the same way in a recipe. If you're trying to make a cake, you're still going to need yeast. You're still going to need flour. You're going to need components. But these guys are sort of given a secondary role. They're not any less important. It's just that writing them this way, we're not saying that that's a solvent. We're not saying that that's not important or not part of the reaction. Showing them above the arrow like this is given the secondary priority because we're focusing on the carbon skeleton that gets us to our product. Now notice something above the arrow here. How many carbons in this little fragment up here? 2. Okay, if I gave it a proton back, like if I added a proton back to this thing, what would I get? Oops. If I gave it a proton, what does this thing form? Yeah, an alcohol. It would be CH3CH2OH. What's that called? 2 carbons as an alcohol. IUPAC name is? Ethanol. Do you know what that would be called as an O- species? Instead of ethanol, it's what do you call it? Ethanoate, yeah? It's an alkoxide. So this is an ethoxide or an IDE type ending. This is our nucleophile. We call this our nucleophile because it is the negatively charged species. When we draw it like this, where we're showing this species, a lot of the times, instead of, like here we've specifically broken this out and we're showing you a negative charge on this oxygen, positive charge on K, which is potassium. Those are on opposite sides of the periodic table, so this is an ionic bond. What we're trying to show here is that this species is chosen as the nucleophile. It can often be written, instead of just like this, it may be written as KOET. That same notation means you have an ionic species, which is an oxygen minus. Anytime coming, especially in this section here, if you see anything like NaOH or lithium O methyl, all of these species, what we're saying, even if they're written out without those charges, those are ionic species. Those are things where you mentally separate the metal part of it from the other component. It's just like if you were to write this, NaOH is made up of sodium and hydroxide. Yes?
So NaOH is like a negative ion that's in a salt with potassium here?
Exactly. So what we have here is it's a negatively charged species. Again, not IUPAC relevant. That's not important. It's not going to be asked to name it. What I'm trying to point out is if you guys are used to seeing sodium hydroxide, and you're like, oh yeah, that's sodium and OH. Well, if it's OR, O anything carbon, same rules apply. An alcohol can lose that proton to make an O minus, so any alcohol can become an O minus something. That's how we get things like lithium methoxide, which is just OMe minus. Mentally, the sodium part of it, the ion, the potassium, this is a spectator. It is not part of the substitution reaction. It's there to balance charge. We can't go and scoop out a jar of only the ethoxide. We have to have ionically balanced systems. So they're added like salts like this. But the business end part of it is this negatively charged species. We could refer to the entire thing molecularly as the nucleophile. The part of it that ends up being bonded to it is this oxygen here. Okay, that's the point I'm trying to really emphasize. This happens with anything that was a heteroatom with a salt. Oxygen with a lithium, nitrogen with a potassium, sulfur with a sodium. Think of all of those as charged heteroatom with a positively charged metal from the other side of the periodic table. These are all ionic. But you're looking at this species here, that's my electrophile. I call it my electrophile because two things. Look at your product. You have made this bond right here. You have broken this bond here. The reactive center, where the reaction actually happened, this is this carbon right here, here. It's the carbon that lost the leaving group, is now holding on to the nucleophile. The nucleophile part of it is that. The new bond you formed is between the oxygen and carbon. You've ejected I minus. I minus is your leaving group here. Okay? So we'll practice through this definition and notation. But the first thing to be able to do is from any one of these reactions, boop, any of these reactions, be able to pick out the bits and pieces. The nucleophile here is this oxygen species. You could refer to the entire salt. The electrophile is your carbon species containing the leaving group. Leaving group is your iodide, the piece of the reaction that got ejected from this reaction as it was being formed. Okay? So, to identify a reactive center, the first thing you have to be able to do is look at your carbon skeleton, find a carbon something bond. The reactive center, as far as the electrophile, will always have this leaving group on it. Most importantly, the substitution reactions we're going to talk about only happen at sp3 carbons. Big underscore. You only have to consider sp3 carbons that are attached to a leaving group. Leaving groups are usually carbon halogen. Generally speaking, though, any carbon to some stabilized anion. These could be things like resonance stabilized or phosphorus stabilized. Anything where that negatively charged species, you look at it and go, oh, I know that species. That is the conjugate base of some stronger acid. Those will be leaving groups. So here in this molecule, the carbon center, the sp3 center, directly attached to my leaving group, bromide, iodide, chloride. Those are the things you're looking for. That will be where this reaction happens. That focuses your attention. The rest of the molecule primarily is coming along for the ride. This is kind of why we practice when we talk about the asymmetric centers. Up until now, we've been practicing, look at a complex molecule, focus on the pieces. The functional group we care about here is that one there. Must be sp3, must be attached to some kind of a stabilized leaving group, okay? So you're looking for these things to come into it. Again, there's some nuance that comes in depending on the specific reactions, but these are the characteristics you have to focus on. So about this guy. If I class this as an electrophile, first of all, why? In your own words, if I called this an electrophile, why do you think that one makes that criteria? What is it about this that you can say, yes, this is my electrophile?
You have the conjugate base of a strong acid attached to it.
We have a conjugate base of a strong acid. More specifically, that chloride, yes, if it was ejected, if I broke that bond, gave those electrons to it, I make chloride, yes. What I mean there is that is my leaving group. I can identify a part of the molecule where if I was to throw out, break that bond, give it the electrons, it leaves as a stabilized anion. That's one part. Do I have an sp3 center attaching to that group, the chloride? Yes. So the reactive site in this molecule will be the carbon immediately attaching to this group. It's not any other part of the molecule. Notice here, do I have another atom with lone pairs in this? Where? Nitrogen. That's just coming along for the ride. That is not part of what I have to consider. It's calling this thing a leaving group and focusing on one center. My eye should be drawn to the sp3 center directly attaching to whatever I'm classing as my leaving group. Again, halogens are your major ones you're looking for. What about this guy? It's an electrophile. Do you see a leaving group?
Yeah.
What is it? Iodide. Okay, now think of another part of this too. If I had to actually draw a bond dipole, look at every carbon in this structure here. The carbon that is currently attached to the iodide, would everybody agree that is probably a delta plus or slightly positive carbon relative to everybody else here? Why? What's the electronegativity? Yeah. Oxygen is polar, that's true. But if I'm talking specifically about this dude, why is that one positive more than I'd say this one or this one even? This is going to be way more delta plus than almost anybody else there. Why? What's that? Induction by who?
The group. The carboxylic acid group.
Okay, carboxylic acid. You're right. There is going to be a little bit of induction. You're talking about induction this way, right? The carboxylic acid is pulling it. It's not a carboxylic acid either. What's that one? What's that functional group? C double bonded O to an H. Yeah, that is an aldehyde. What I'm getting at is this center here, that carbon is also delta plus. You actually have two delta plus centers in this molecule. Only one of them will participate in a substitution reaction. So we have a delta plus here. I'm going to call it number 1, and delta plus here, number 2. Why will the substitution reaction have to happen at number 1 and not number 2? What's the hybridization at number 1?
sp2.
At number 1?
sp2.
And number 2?
sp2.
Substitution reactions must occur at sp3 centers. This here, your center there, is your reactive center for a substitution reaction. Why is it positive? There's 2 reasons. Carbon versus iodine, which is more electronegative? So there's going to be a small bond dipole, right? Iodine is sort of tugging on this bond this way. To give a bond dipole by induction, I can still consider that, right? The iodine is going to be more negative relative to the carbon because it is more electronegative. That single bond is going to have a slight polarized charge. Same thing is here too. This here, this is going to have a bond dipole. Oxygen is more electronegative than carbon. So you're going to have a bond dipole that's going to be slightly positive here. But for substitution, my eye should focus only on this center. That's the center that has my leaving group, a group that can break away as a negatively charged, and it is my sp3 center, not the other one. There's other chemistry we can do at this other one, this carbonyl. What about this one? Is this an electrophile? Do I have what looks like a leaving group? Is it attached to an sp3 center? No. That is my carbon. It's bonded. This is not sp3 hybridized. There is no substitution possible at a carbon like this. An sp2 center like this with a leaving group attached. Yeah, it's a leaving group. Could be considered a leaving group. Not going to be part of an SN2 reaction or an SN1 reaction. No substitution can happen here. If I really want to substitute that, I've got to go to a whole other class of chemistry. But the substitution reactions we're talking here will not work on this one. So the rules we're laying down here mean that now, depending on the molecule I want to build, I can choose molecules with certain kinds of groups in certain positions in order to achieve certain goals. It means that if I wanted to do a substitution reaction, I can take a molecule that has a carbon-bromine on an sp2 center, and I'm safe knowing it will not react. Compared to a carbon-bromine on an sp3 center, that will react. So by choosing where to decorate my molecule, where to put these leaving groups, I have control over what happens at what center. So this will not participate. This is not a viable electrophile, will not react. Okay, so look through this. Where do you expect nucleophilic attack to happen? The other way when you say that is, where is the reactive center? Where's the carbon where the nucleophile will attach to when you're done? All right, everybody all together on 3. It is B. The carbon which contains, is holding on to my leaving group. What is my leaving group here? A, B, C, D, or E? The leaving group is? Yeah, this would be my leaving group, the thing that is going to be displaced, leaving with that charge. So all substitution reactions, we have these two mechanisms. The overall reaction is identical for both. You must have a nucleophile, you must have an electrophile. The electrophile will have a reactive site, and will have a leaving group. That is common no matter which kind we're talking about here. But this is where we're going to differentiate. There are 2 different ways of doing a substitution reaction. What we call SN1, which is a unimolecular nucleophilic substitution, and SN2, a bimolecular nucleophilic substitution. The mechanism is different. And what's interesting about this is where we begin to apply that level of control. Now, we've had some conversations after class, and people have asked me, based on chirality, okay, yeah, you talked about how important chirality is, but molecules will do whatever the heck they want. How could we possibly control it? This is how. By choosing certain reaction conditions and certain substrates, I can force the molecule to go by an SN2 reaction versus an SN1 reaction. And the really cool thing is, those 2 mechanisms have different rates, they have different consequences, they work depending on what substrate you choose. So this is what is going to be most important. Now first, we're going to talk about SN2. Everybody all together, SN2, I want you to put up your hands. And SN2 goes like this. How many times did you make a noise? SN2 reactions have a single transition state. They happen in one step, and they're done. They're surgical. They have a single transition state. What does that sound like when we talked about kinetics? Things that have one transition state are also called elementary processes. It involves how many molecules when we do this? This is a bimolecular elementary process. SN2 reactions are simple mechanistic because they take 2 things in one transition state to make 2 products, right? 2 things go in, 2 things come out, but one step, okay? The general reaction looks the same. What you come in with, what you go out with. This does not change. What we call things the same. There's a nucleophile. There's the electrophile. Electrophile has a reactive center and a leaving group, okay? But this is what the mechanism looks like. Actually tracking where the electrons go, this looks a lot like acid-base reactions. Your arrows start on your negatively charged species. In an acid-base reaction, that's our base, right? The negatively charged thing. They go towards the carbon, where the reaction is happening. As that carbon is accepting those electrons, we're saying 2 electrons go to that carbon, It means we're forming a bond between that oxygen and that carbon. But how many bonds does that carbon currently have? Does it have a full octet right now?
Yes.
So if I'm going to accept electrons from that oxygen, I've got to dump electrons at the same time. So just like an acid-base reaction with a proton, if you form new bonds to that center, you must at the same time eject electrons. They go off, and those electrons leave with the chlorine. Okay? I used to use a dating analogy for this. This is serial monogamy again. Carbon is in a long committed relationship with that chlorine. Then oxygen comes along, and that looks a lot better. Oxygen makes the offer. Here is what I'm proposing to you. Carbon says, that's cool. Chlorine, take your electrons and go. All in one shot. There's never a point in time where there's some weirdness going on. There is only new bond, old bond, one step. Okay? And this goes to the left, to the left. So, most important here, one transition state, 4 electrons, bond form, bond breaks, all in one step. This happens by what's called backside attack, or Walden inversion. This is the first really weird thing that you guys are going to see. What's the geometry around that carbon with the chlorine? It's sp3, so what shape is it? It's tetrahedral. But if you notice, and we've drawn it specifically for this reason, for a very good reason. Look at the chlorine, the carbon chlorine. We've pointed the chlorine facing from the right, from the left to the right. The hydrogens are sort of pointing off in this direction, like an umbrella. When the reaction happens, the oxygen comes in, and it comes in exactly 180 degrees from this bond. This trajectory is not by accident. This is on purpose. It's because, like we said before, the carbon already has a full octet. But the carbon is slightly delta positive, right? The carbon-chlorine bond is polarized. That gives it the opportunity to have a little bit of a positive charge on it. That targets the oxygen minus towards it. But it doesn't come in randomly from any geometry. Just like billiard balls, the oxygen, carbon, and chlorine line up. When the oxygen punches in to attack that carbon, the carbon-chlorine bond will release. And it happens just like billiard balls. One goes in, one pops out. It has to be lined up this way because what happens to those hydrogens, not easy to see here, but the hydrogens that we're facing this way kind of go through this intermediate where it's actually flat. It looks kind of like a what we used to call a Texas carbon, 5 things attaching to it just for a transition state. That carbon in the middle actually flips itself inside out. Okay? It actually will invert itself. Again, back to dating analogy, sometimes you want to be with somebody so much you will turn yourself inside out to make that happen. That is what happens to this center. Now again, if there's just hydrogens here, this does not actually, there's no way to see that it happens. But when that center is asymmetric, this is where we'll see it. We'll come to that one in just a second. So, let's draw the mechanism. And from the mechanism, predict the product. First thing, who's the nucleophile? Who's the electrophile? The electrophile is, yeah, this thing right here. Where is the reactive center? The reactive center is this one right here, attaching to the bromine. That makes my bromine my leaving group, right? Those are the pieces of it. The nucleophile is all of this, but most importantly, this is the part you should focus in on. The nucleophile molecule, we can call it the whole thing. We can focus on that methoxide, right? The oxygen minus with the methanol. It's the base of methanol. Sodium is just our counterant. This is coming along for the ride. So, when we're drawing the mechanism for this reaction involves the nucleophile is the one that kicks things off. Electrons from here are going to form a bond to that center. Now, even though they're not drawn in that arrangement, in your mind, remember, oxygen, reactive center, leaving group, all have to line up 180 degrees to each other. When this is approaching, that center, oxygen to here. We're not done yet. This says there's a new bond between oxygen and carbon. We also must have, second pair of electrons, carbon to bromine. Just like acid-base reaction, there's a total of 4 electrons moving, 2 arrows. All SN2 reactions must have at least these 2. This is the substitution portion. So the products of this reaction we have to draw out. First thing we're going to do, make sure the carbon portion of your starting material was 4 carbons. Your product had better be 4 carbons. The reactive center was this guy here at the end, and we now have a new bond, 2 oxygen, methyl. You don't have to draw in all the electron or the lone pairs, but for keeping track, this is what we've got. That other third pair of electrons is now actually here. It's contained in that bond between my reactive center and the oxygen. We're not done. This is the business end of it. Yes? You can draw a line, a stick line. I look at it like this. That, you mean CH3, you mean methyl. That is definitely methyl. That's all. But yeah, you can draw just a stick out into space. That is totally cool. Means the same thing. Okay, that's the business end. That's the product of the reaction. We're not done yet because remember, we want to express all the elements. We want to make sure that we have a balance here. There's going to be a sodium. Because sodium came in, you can draw that as a spectator ion. It is not. If you left off the sodium, that's not that big of a deal. A lot of the times, organic chemists, we know sodium is just a spectator ion. That is not a big deal. If we say specifically, show absolutely everything, yes. But this is one of those things. The reason I put it up is, if you're reading organic chemistry literature, if you're looking at other problems, our convention is this was not really important to the reaction, so it may not show up in your reaction in terms of your products. What does matter, though, is the thing here. Whatever that thing you kicked out, showing the leaving group is important because we want to make sure that we keep track of where did we displace. Some leaving groups are complicated. Some leaving groups can actually come back and do other chemistry. So that usually is something we pay attention to. And again, this is partly convention. If you want to be 100% right, definitely include all the atoms you have on one side should balance the other. This is also just for bookkeeping. The charge should also match. If I started off with a neutral species, ionic species and a carbon species, the product is going to be ionic species and some other covalent species as well too. So we have a leaving group, the bromide, we have a new bond, we have our spectator. This is our product here. The mechanism involves 2 arrows, nucleophile in, leaving group out. Yes?
Would you ever have the sodium bond to the bromide?
Sodium bonded to the bromide? You could express it like that, but again, what kind of bond is that? If I drew this, instead of sodium plus bromine minus, if I just drew this as NaBr, like this, what kind of species or what kind of bond is that? Still an ionic bond. That is totally fine to draw it this way too. In the same way, ionic species like this could be drawn as NaOMe. That is the same thing, okay? If you want to draw them ionically separate, also fine. Any other questions on that? So SN2 reactions, nice part about them is, mechanistically they're relatively simple. We start off with 2 species. We end up with 2 species. It happens in a single transition state. Oxygen attacks carbon. Carbon kicks out chlorine. 2 products. Okay? What this means, though, for kinetics, what we said, remember, was this is a bimolecular elementary reaction, right? If it's a bimolecular elementary reaction, that must be the rate law. If we're doing an SN2 reaction, and it's a bimolecular reaction, and it is elementary, you can draw the rate law implicitly off of this. It always, SN2 reactions will always have some K times the nucleophile concentration times the electrophile. They are all like this, and this is one of the hallmarks of SN2. If I'm trying to interrogate a system and figure out, is it going via an SN2 reaction, that has to be its rate law. It must respond, the rate will get faster if you change the concentration of nucleophile or electrophile. It is a second order process, okay? So, what about this guy? I'm going to double the concentration of sodium methoxide. What happens to the rate? Okay, on 3. 1, 2, 3. Answer is D. It doubles the rate of product formation because if we look at this, and if we told you specifically this is an SN2 reaction, that means rate is equal to K. In this case, I'm going to call this guy A and this guy B. A or B, as I've drawn. Who's the nucleophile? Who's the electrophile? What's the leaving group? There we go. See, it's that creepy, this is the last week where everybody's sort of in that nice monotone. I love it. Creepy chant. A is my electrophile, has bromine. Reactive center, right there. This is my nucleophile. Methoxide's the business end. It's going to involve concentration A, concentration B. If it's an SN2 reaction, both components matter. Nothing happens without these two, and they both are going to react in a single step. It is a bimolecular elementary reaction. So yes, the reaction will double. What if I increase the concentration? Product of this will look like OMe. Yes? That looks good? I'm going to call that C. What if I double this guy's concentration? What happens to the rate of reaction if I double the concentration of my product? Nothing. It's not part of my reaction. What if I change the temperature of this? Depends which way you change the temperature, absolutely. Heat it up, it's probably going to go. Cool it down. What if I did it on the moon? Yeah, okay, don't. Fun fact, we actually might get to do some stuff at ISS later, provided ISS still flies. Zero gravity crystallization is a thing. This is really cool. Anyway, this is our transition state. So like we started before, what does an SN2 reaction sound like? It sounds like more than that. It sounds like, there you go. One transition state, two things go in, one thing comes out. Usually, the delta G of these reactions is negative. This is the prototypical profile of an extensive reaction plot for an SN2. That's why we know it's a bimolecular process. That's why we know it's a single transition state. It follows this rate law, okay? So all these things, just like we talked about strong acid, strong base, delta G, kinetics, all these things fit together. Knowing it's SN2 means this is the reaction profile that you're focusing on. Now, the weirdness. This backside attack thing always happens. Just because the center is these hydrogens, see the hydrogens we show here on this side, they're kind of umbrellaing over here. As the nucleophile approaches, the transition state, what's sitting at that very top apex of the profile, looks like this. Remember, transition states are not isolable matter. They're rearrangements of electrons, they're rearrangements of the bonding of the thing. They can be weird, and they do not stay like that for long. That's why they're at the apex, right? The transition state exists right there at the top of that energy curve. We know it must pass through that one, but there's no way you're going to be isolating that guy in the middle. That's as close to we get as our Texas carbon we get here on Earth. It has, my hydrogen bonds are all in place. Those were not part of the substitution. But notice the new bond you're forming between oxygen and carbon, it's starting to kind of come in close. The oxygen is approaching that center. Meanwhile, the carbon-chlorine bond is on the way out. It's a little bit longer than it normally used to be. The bonding order, instead of being 1 for carbon to chlorine and 1 for carbon to oxygen, it's half-half. It is a transition between these two. It's a handoff. But because of this arrangement, as the oxygen approaches from left to right, what happens is those hydrogens must kind of get out of the way. The repulsion that happens from this nucleophilic oxygen, those electrons coming into that center, it must approach along that back side of that carbon-chlorine bond, and because of that, the carbon is actually going to umbrella out to this flat kind of intermediate, and when it's done, it's actually inverted itself. This is an umbrella on a windy day. It's popped itself inside out. So even though here, there's no record of it happening. We don't have a signature we can look and say, oh yeah, that definitely looks different, other than the diagram we've provided here. But when you have, if, and this is, write this down, if the reactive center is an asymmetric carbon, and you're doing an SN2 reaction, you will notice. If the reaction is happening at just a normal carbon, CH2, something like that, it's invisible. The reactive carbon here is which one? That one. Again, why do we use IUPAC? What carbon number? What? I'm so sad. Name this. What is this in terms of how many carbons? This is two? Yeah. How many carbons is the longest carbon chain? Five? 1, 2, 3, 4, 5. Cool. We are a week and a half from the final. 5 carbons. I know. Okay, 5 carbons, yeah? So what is this? This is a pentane. Carbon number what has a chlorine? Carbon? Okay, is it R or is it S? Okay, this is a pentane. It is a 2-chloropentane. If I had to number these, hydrogen is 4, chlorine is, what's number 2? Methyl, or 3 carbons is called a propyl. So methyl will probably be 3. This is going to be 2. All right. Is the lowest priority group away from you towards you in the plane? So is this, grab the number 1, go to number 2. Are you making a left turn or right turn? So this is S, 2-chloropentane. This is a single geometry, single stereoisomer. We have an asymmetric center. The reaction is happening. The reactive site is this dude here. That is my S center. If the carbon has this chirality, this geometry, this is where now you will know this backside attack is happening. When we first started looking at substitution reactions in the annals of history, and we started seeing this happening, that's why we know this inversion is going on. What happens here? The leaving group is attached to my reactive site. That's the bond we have to break. If that bond, the carbon reactive site, is an asymmetric center, this is where that inversion will matter. Because remember, look at this geometry. As I've drawn it here, the nucleophile is going to approach along this trajectory. I'm going to draw this as Nu minus. If it approaches along that trajectory, the chlorine is going to leave there. That center, hydrogen, methyl, propyl, is going to flip itself inside out. The nucleophile is coming in here. As drawn, it's going to look really weird. But again, it's going to umbrella. It's going to change its geometry. Nucleophile is coming in. It will change this site. So why does that happen? This goes back to our bonding theory. Remember, this here, this is our frontier molecular orbital picture. The hybridization on my carbon was sp3. So this represents my sigma bonding orbital. That's my sp3 hybrid orbital on carbon, showing a sigma bond to my chlorine. That's what's holding this thing together, right? Electrons are being shared between the chlorine and the carbon. That is the foundation of this bond, right? But I need to break this bond. Where do the electrons go? That bonding electrons by our arrows, where do these electrons go? Do they stay in the carbon or do they leave with the leaving group? Remember, when we draw this mechanism, we draw it where, back here, nucleophile goes in, chlorine goes out. We're saying that the electrons in the bond that we're breaking are departing with my chlorine. They're leaving there. So this orbital is what's holding the chlorine and carbon together. It's the foundation of their relationship. But the nucleophile does not care about the bonding orbital. It cares about the antibonding orbital. Remember way back, what was an antibonding orbital? What's that?
Higher energy.
It's higher energy. Usually, does an antibonding orbital have electrons in them?
No.
That usually, if we populate an antibonding orbital, we weaken the bond. Because antibonding orbitals have a node along this bonding axis. So what we're doing is, the starting material, the electrophile, has a carbon leaving group bond. That is my sigma bond. The bond, in order to break that bond, the nucleophile is going to target the antibond. It's not playing with the bonding orbital. It looks and says, hey, there is a currently empty antibonding orbital. The antibonding orbital geometry looks like the sigma bond. It has the same presentation. It's along that bonding axis, except there's a node between the two, and more importantly, there's a lobe right here. This is the site where my nucleophile is going to approach. The nucleophile comes along with its electrons. It adds those electrons to this antibonding orbital. That weakens the carbon-chlorine bond. That's why this geometry matters. The lobe here, where that carbon presents that orbital, that antibonding orbital, that's the target, like bullseye, that goes on the carbon for the nucleophile to approach. That's why it has to happen along this 180-degree plane. It approaches from this center because that's the site where, if I add electrons to this center, I weaken the carbon-chlorine bond. I strengthen it up because I'm adding electron density there. The other way to look at it, the carbon, like we said, is going to have a bond dipole. The bond dipole, chlorine is more electronegative than carbon. As a result, there's a carbon plus, or delta plus, left behind. Induction says that carbon will be slightly more positive than any other carbon in this center. That's why this becomes the target. That's why this is the reactive site. Okay? So this bonding geometry gives us why that carbon is the target, electron density. And it also says this is why the nucleophile has to approach along this 180-degree core. We need to add electron density to the carbon-chlorine antibond in order to fracture it. Yes?
So adding electrons to the anti-bonding orbital creates like the orbital between the Cl and the carbon?
Exactly. If you think of the only reason this carbon-chlorine bond exists is, remember, if we just focus in. Let's go back to the hydrogen example. If you guys remember before, hydrogen, hydrogen. It has a 1s and a 1s. These are the two separate atoms. They both come in with a single electron each. One hydrogen atom and one hydrogen atom. When we want to form a molecule, these two separate orbitals can be combined in two ways, what we call productive and destructive. If we bring a 1s and a 1s together, I can make my sigma, and I can make my sigma star. The geometry, the sigma orbital, looks like this, where there's a nice electron density between the two, and the antibonding sigma star looks like this. There's a node between the two. Those are the geometries based on how we choose mathematically to add those orbitals together. Productive addition gives you extra density. Destructive addition causes a plane. Now, both of these are orbitals. Each orbital can have two electrons. The sigma orbital gets populated with the two. Each hydrogen brings one. We form the bonding orbital. We form a stable bond. Hydrogen, hydrogen has a sigma bond together. If I want to come along and I want to fracture that hydrogen-hydrogen bond, I could add electrons. If I add electrons to this orbital, what I'm doing is now I'm taking the productive relationship between these hydrogens and I'm dumping in electrons to the destructive relationship. As a result, the molecule will split. That's how, and again, this is one model for thinking of how bonds form. Bonds form because electrons are donated to more stable orbitals. Empty orbitals that are good for bonding get populated. How we break bonds, you populate antibonding orbitals. By putting electron density into something that creates a node between those electrons, what you're doing is you're creating a rift between the two. So, when we do this, the nucleophile will add density here. That does two things. The lone pair from the nucleophile putting in this electron density weakens the carbon-chlorine bond here. But it also, very selfishly, creates a new sigma bond between nucleophile in what we called the antibonding orbital. Remember, it was only called antibonding with respect to this carbon-chlorine. As soon as the chlorine leaves, that is now the new bonding orbital between nucleophile and carbon. It's handing off these two. So by adding electron density into this antibonding orbital, we eject the chlorine and we form a new sigma bond to nucleophile and carbon. But in doing that, the geometry has to change. This center must invert. So if this has different priorities, we've just numbered them off here. If 1 is my nucleophile, 1 prime, and we've got, as drawn, 1, 2, 3, 4, that is an R center. If the nucleophile comes in, 1 prime is coming in, 1 is leaving. That's my leaving group. The new geometry we have when we've done this, if you look, this priority replaces this one. We've now created an S center. This inversion means nucleophilic attack, SN2, at these centers creates a change in the chirality. Okay, we're going to kick off here. Next class. I'll see you guys on Wednesday.